Today we're going to be solving absolute value inequalities, and we're going to start by just reviewing again what's the definition of absolute value. So the easiest way to think about absolute value is just to think about distance from zero on the number line. Distance from zero on the number line. If that's our working definition of absolute value, that is a good way to visually understand what absolute value is all about. When we first talked about absolute value, we talked about the whole idea of what is normal, and we looked at a specific application of the body temperature of a human. It's normal. Perfect temperature, according to doctors and scientists, is 98.6, but a normal range is anywhere from 0.5 below to 0.5 above. And anytime that we're talking about trying to find a normal range, that's when we use absolute value inequalities. So absolute value, the distance from zero on the number line, and we've got a little chart here to fill in. So these are our x values. They're going to be our input. And we're going to plug them in to the absolute value bars. And remember, absolute value bars are grouping symbols. And that's going to give us our output. So if x is -3, the absolute value of -3, and I'll write it just on this one, absolute value of -3 is 3. Why? Because -3 is 3 units from 0 on the number line. If we plug in -2.5 into the absolute value bars, we get +2.5. Why? Because -2.5 is 2.5 units from 0 on the number line. Plug in the -2, we get +2. Plug in the -1, we get 1. Plug in the 0, we get 0. Because how far is 0 from 0 on the number line? It is 0 places away from 0. If we plug in 0.5, we get 0.5. If we plug in 1, we get 1. 1.5, 1.5. 2, 2. 2.1, 2.1, 3, 3. So what we're seeing here, and I'll even highlight it, every single time we get a positive result. Why? Because distance is a positive measurement. It doesn't matter if we're walking forwards or backwards, we're covering a positive distance. So absolute value is distance from 0 on the number line. So we filled in the chart. Now we're going to go back, and I want us to circle, we're going to circle all the values of x that make this inequality a true statement. And remember, that's our essential question. Every time that we have an inequality, we're looking for what values or answers or solutions, those are all kind of synonyms. We're looking for values that will make this a true statement. That's our essential question every time we solve an inequality. So the absolute value of x is less than 2. So which of these values in the bottom row are strictly less than 2? Is 2 less than itself? No, 2 is exactly equal to itself, so 2 will not make it true. 2.5 will not make it true. 3 will not make it true. 1 will make it true. 0 will make it true. 0.5 will make it true. 1 will make it true. 1.5 will make it true. So basically, it's these numbers in the middle that are going to make it true. So now let's shade that solution set on this number line. So based on what we already know, And looking at what we've got here, we'll put 0 in the middle. We'll put 1, 2, 3, -1, -2, -3. Remember, make number lines work for you based on what your solution set is. So 0 works. Negative, and remember, these are the values that we input. So this is what we have to think about. So -1 made it true. 0 made it true. 0.5 made it true. Remember, 0.5 is right in the middle between 0 and 1. 1 made it true. 1.5 made it true. 1.5 is right in the middle between 0 and 2. And I don't have it on here, but -1.5 would have also have made it true. So what we're seeing here, and what we're seeing on the bottom as well, is that it's everything in between -2 and +2. Once we input those values, our output is all less than 2. So open circle on the -2, open circle on the +2, and shade everything in between. So this is the solution set that represents this particular information, and it represents this inequality. Now, based on what we learned in the previous section, this is a conjunction. This is an and situation. So let's keep looking here, and let's keep answering questions. All right, so actually I think I will use incredible technology and fold this paper down so we can see all that's happening here. So here's our number line. So is the value -1.9 included in the shaded region? So -1.9 would be just before -2, and yes, it is included in the shaded region. So yes, and why or why not? Well, why? Well, the absolute value of -1.9 is less than 2. Why? Because 1.9 is less than 2. That is why -1.9 is. So it satisfies that essential question. Is 2 included in the shaded region? Well, everybody take a good look. 2 is underneath an open circle. And remember, that open circle is not inclusive. The open circle is not inclusive. And if we think about it in terms of a logic statement here, is the absolute value of 2 less than 2? Well, is 2 less than 2? Think of that as a question. No, 2 is not less than itself. It's equal to itself. So is 2 included in the shaded region? No. No, it is not. And there's the reasoning why. Because 2 is not less than itself. So if we were to describe the number line and its shaded region, if we wanted to describe that verbally, it's a conjunction. So we could say all numbers that are greater than -2, and remember, and conjunctions are and situations, greater than -2 and less than +2. So that's how we would describe the number line and its shaded region. If we wanted to do that algebraically, we could do it with an inequality that looks like this. We could say, well, x is strictly bigger than -2, but it is less than +2. It's in the middle. It's in the in-between. It's in the overlap because it's an and situation. Now, let's look at another question. Let me fold my handy dandy paper here so you can read the question. So, how would the number line look differently if the inequality was changed not to be strictly less than 2, but the absolute value of x is less than or equal to 2. If we changed it to or equal to, would those circles be open? No. The circles would be shaded. The circles would be shaded, and when the circles are shaded, it would mean that x could be equal to -2 and x could be equal to +2. Because that or equal to, the shaded circles would be inclusive. So that's what would make it different. Next, how would it change it if it read the absolute value of x is greater than 2? Well, let's think about this, and I'm going to draw a whole new number line right down here. And let's think about what's happening here. Our original inequality was less than. When it's a less than and we have an overlap of the two sets. And think about it this way. If the definition of absolute value is the distance from 0 on the number line, when does absolute value get smaller? Absolute value gets smaller the closer and closer and closer you get to 0. So as we get closer to 0, absolute value decreases. As we go in opposite directions, a disjunction of sets, absolute value is going to increase. So how would it change the graph if it read the absolute value of x is greater than 2? Well, it would change it dramatically. Because instead of our solution sets coming together, our solution sets would go in opposite directions. So it would still be open on the +2 and the -2, but instead of shading in the middle, if I want my absolute value to get bigger, greater than, if I want a greater absolute value, I'm going to have to shade farther away from 0. So absolute value gets bigger the farther you go away from 0. So that's when absolute value gets bigger. Absolute value gets smaller the closer that we get to 0. Absolute value gets bigger the farther you go away from 0. So if we have the absolute value of x is greater than 2, that will create a disjunction. When we have the absolute value of x is less than 2, we have a conjunction. It's an and situation. This is, of course, an or situation. One set or the other would make it true.